right. Good morning, everyone, and thank you for joining us for another installment of the Long Coffee Break. My name is Billy Donovan. I'm a sales engineer based out of Littleton office, and today I'll be giving you the rundown on gas phase filtration. It is my hope that after today's presentation, you'll have a better understanding of how gas filtration works, common applications, and the types of gas phase filters that are available. So first things first, what type of filtration are we discussing today, and what do we actually call it? Is it gas phase? Is it molecular, carbon, charcoal? All these names and a few others have been floating around our industry for years, and they all describe the same thing, a filter that removes contaminants at the molecular level. So strictly speaking, molecular or gas phase filtration would be the most accurate description, but these terms don't exactly roll off the tongue, and few people associate these names with the actual process. For the sake of simplicity, I'm just going to be using the term carbon filter or carbon filtration from here on out. It's a bit of a misnomer because activated carbon isn't really the only type of filter media, but it's a term that most people are familiar with, and yeah, that's good enough for me. So, removing contaminants at the molecular level. What exactly does that mean? Well, let's first start by looking at the filters that we use for particulates. ASHRAE style filters are going to capture most of the particulates on this chart. Those types of filters are going to be your MERV 8 fleets all the way through your MERV 16 finals. Those MERV 8s are doing a lot of the work here in that 3 micron and up range. Your MERV 16, those are going to be about 95% efficient, at least against 0.3 microns and up. So pretty much all of this left-hand side of the chart is kind of well taken care of. For greater efficiencies at the smaller particulate levels, we use HEPAs and ALPAs. An ALPA can be, for example, 99.995% efficient at a 0.12 micron size, or most penetrating particle size. But gases, on the other hand, are much smaller than the particulates that we use HEPAs and ALPAs for. About 10,000 to 1,000 times smaller than those sizes of particulates. So there's just no way that a HEPA filter or an ALPA filter is going to be able to capture a gas. It's just not even close. All right, so how can we filter contaminants on the molecular level? Well, we can accomplish this by using a media with a large surface area like activated carbon, and then drawing upon the process of adsorption. Adsorption is when molecules stick to a surface. Absorption, with a B, is when molecules are dissolved or diffused into a substance. Basically, we use carbon because it has an extremely porous structure, and that large surface area enables a large capacity for the process of adsorption. Molecules passing through carbon media will stick to the carbon surface, filling its pores. And when the surface of the carbon media has been entirely covered, then the molecular contaminant will freely pass through the filter and should probably be exchanged or replaced at that point. Just to give everyone a little bit of some perspective, 1 gram of activated carbon has a surface area of approximately 1,000 to 1,500 square meters. So that's like 10,700-ish to 16,200-ish square feet. 4 to 5 grams of activated carbon would have a surface area equivalent to a football field. Awesome. So now that we know how carbon filtration works, let's take a look at some common applications. Generally speaking, gaseous contaminants can be categorized as odorous, corrosive, harmful, or toxic. Most people think of odor control when it comes to carbon filters. So let's start there. Terpenes from cannabis facilities, food smells, wildfire smoke, all good examples of nuisance odors that are not necessarily harmful or damaging, but can have a big impact on occupant comfort. But there's a lot more to carbon filtration than just mitigating odors. Corrosive applications can generally be found in the industrial arena, wastewater treatment plants, pulp mills, refineries. These types of facilities typically emit high concentrations of corrosive gases like hydrogen sulfide. H2S can corrode the printed circuit boards in electronic equipment. So these types of facilities typically have some sort of carbon filtration system serving their control rooms. The last thing you really want is, your important equipment failing at those types of facilities. It may sound strange to some of you, but museums and archives have corrosion challenges as well. Many of them use carbon filters to protect artwork and artifacts from corrosion and oxidation. The harmful and toxic application area spans across many different industries. Some examples are, hospital helipads and airport terminals are generally challenged with Jet A fumes entering their outdoor air intakes. IVF clinics are concerned about VOCs that are just in the outside air because of pollution. VOCs have been shown to diminish their success rate at IVF clinics. Microelectronic manufacturing clean rooms require protection from molecular contaminants. Pharma companies researching or producing radiopharmaceuticals need to scrub their exhaust air. Nuclear power plants, for obvious reasons, need to remove radioactive compounds, and so on and so on and so on. Carbon filters can be used in many different areas. So for whatever your application, we likely have a solution for it. For those odorous applications, AAF makes an ashtray style filter. So you still get those MERV 8, MERV 13, MERV 15, whatever efficiencies, but you can combine that with a carbon media. Nice about this is, when wildfire season gets started, an owner can simply just go up to their equipment and replace their regular filters with some of these carbon fleets or a carbon final, and everybody's happy. For those corrosive and harmful and toxic applications, AAF has some more specialized solutions. Cassettes and cylinders that can be placed into specialized housings or integrated into air handlers. Hegas and deep bed scrubbers, AF's got the whole gamut covered. So on top of all those different solutions, there's a ton of different types of media. Like I mentioned before, carbon is kind of a misnomer. There's a lot of different medias. You can get chemical impregnated carbon. So potassium permanganate is a pretty big chemical that's used. It's really effective at capturing, the corrosive gases like H2S. Activated alumina is another one that's pretty popular as well. You can get these in various blends or to certain specifications that you want or an end user wants. So two of the most common questions I've gotten over the years regarding carbon filters are, how long will my carbon filter last, or how frequently should carbon filters be replaced? And the answer to that really depends on a lot of different factors. It could be, you need to know chemical concentrations, operating hours, local environmental conditions, and so on. Carbon filters don't load up in resistance like particulate filters do, so you can't really use resistance as a gauge of capacity. For the more critical applications that we discussed earlier, the primary way to determine the expected life of a carbon filter is to monitor the media capacity over time. What we do is we just take samples of the media that's been used. We send it into AAS Lab, and we can chart or plot capacity over time, and really that allows us to create a safe and accurate service schedule for the end user. For the odorous applications, most end users go with the nose test. So it's just, oh, that XYZ or smells back, I'd better go up to the rooftop and put some fresh filters in. The other common question I get is, what type of media should I use? I just kind of showed all the various medias that are available in that previous slide. And again, this really depends on a number of factors: the application, the target contaminant, the concentrations, the operation hours, et cetera. It all sounds like a lot of work. Some people just don't want to think about it, and they want to use a blended media or a broad spectrum media. And while that's not necessarily wrong, it will still work in the beginning. By selecting a media based off of your specific application, we can ensure that you're getting the greatest capacity at the most economical price point. So yeah, just let Long and AAS help you figure those things out. Well, that's all I have for today. Thank you everyone for attending. If you have any questions regarding carbon filtration or anything filter related, please reach out to your Long salesperson. And moving on to that, it's time. Prizes this week are a $100 Go Play Golf gift card, a Fitbit Inspire 3, and with Valentine's Day coming up, we have these lovely Golden Girls rings. Please join us next week for our VRV Best Practices series, where our very own Andrew Schmidt will be talking about VRV design. Thanks everyone, and have an awesome day.